Hello, my name is Stuldreher, and I'm glad you joined the presentation Unsupervised Clustering of Groups with Different Selective Attentional Instructions Using Physiological Synchrony. The work that I present here today has mainly been conducted by the first author, Alexandre Merasli, but unfortunately he cannot join, so I will present today's work. Here's a short outline of today's presentation. Let's first dive into the background. Physiological signals such as EEG brain potentials, heart rate, or skin conductance have long been known to be informative of mental states such as emotion, cognition, and attention. In recent years, a shift in these studies has shown, moving from monitoring signals from only one individual to monitoring signals from multiple individuals simultaneously, and then assessing the similarity between the signals over time. This similarity between these signals is often referred to as physiological synchrony, and recent years have shown that the degree of physiological synchrony is informative of shared attentional engagement. And recently, we found similar things in our own studies. We presented a group of individuals with an audiobook that was interspersed with short sounds that were emotional sounds and beeps that attending participants had to keep track of. So whereas all participants heard exactly the same, we varied the attentional instructions between participants, whereas half of the 26 participants were instructed to focus on the audiobook and try to ignore all the interspersed stimuli. We instructed the other half of participants to focus on these interspersed stimuli and try to ignore the audiobook as best as they could. Our research question for them was, what if we pick one individual out of this group, of which we then don't know the attentional state? Can we determine the attentional state based on physiological synchrony with the two groups with known attentional focus? And as the results on this slide show, we could do that very well, especially for EEG, in which 96% of the 26 participants could be correctly identified. But also very interesting in this field of research then, was that skin conductance and heart rate also showed very positive results. So whereas this is very nice, it may not be reflective of real-world environments, because here we had to do that we knew the attentional state of part of the group. But in real-world environments, it's often the case that there's a group of individuals of which you don't know anything about the attentional state. And that is where the current work comes in. In the work that I present today, we had similar research aims, namely to correctly identify the attentional state of individuals in a group, but now without any knowledge of the attentional state of any of the individuals. And in general, we here had two research questions. First, how does clustering performance depend on the type of physiological measure used? And second, how does clustering performance depend on a specific unsupervised learning technique used? Let's dive into a bit of the methods for today. The scheme on this slide presents the processing pipeline used in the current studies. After signal recording, we had to process these signals and then use different unsupervised learning techniques, here referred to as mapping and clustering, to identify the shared attending individuals in this group. Afterwards, we evaluated performance in two different ways, which I will go into later. First, dive a bit into the signal recording. We used here the same dataset as the ones for which I presented the results in the backgrounds before. We recorded signals from 26 participants that were all listening to an audiobook that was interspersed with short stimuli. 13 of these participants were instructed to focus on the audiobook, and 13 were instructed to focus on the short stimuli and try to ignore the audiobook as much as possible. We recorded EEG brain signals, skin conductance or EDA, and heart rate. In the processing phase, we computed the physiological synchrony for each of these individuals. And this resulted for each individual in a value of synchrony with all other individuals. And this is somehow some measure of similarity between these individuals. To apply the clustering algorithms, we converted this similarity into a distance. So persons with high physiological synchrony had low distance between each other, and persons that had low physiological synchrony had a high distance between each other. Various ordination methods, or more simply referred to as mappings, have been proposed for distance matrices. And this mapping is complementary to clustering in such way that the objects are ordered so that similar objects are near each other and dissimilar objects are farther away from each other, theoretically enhancing clustering performance. We here used varying mapping algorithms that are depicted on the slide here that can be divided in two blocks, namely one for unimodal and one for multimodal. Namely, we investigated the performance of each individual measure, that is EEG, heart rate, and skin conductance, but also for all measures combined in a multimodal fashion, as we expected that would maybe increase performance compared to unimodal clustering. We then come to the clustering algorithms. As you can see on this slide, we used 4 different clustering algorithms in this study. And we did this to try to see how clustering is dependent on the specific algorithm choice, because especially in our field of research that is focused on mental state monitoring, the knowledge of these clustering algorithms varies strongly between researchers. So it's good to investigate how the choice of algorithm can influence the performance of the clustering. That brings me to the evaluation phase, where we try to evaluate the clustering performance. We did this in 2 ways. First, of course, in this study, we had the ground truth labels available because we know which participants were instructed to focus on which aspects of the experiment. However, we also tried to explore a more unsupervised evaluation that is often referred to as the silhouette coefficient. And this silhouette coefficient is a measure of clustering performance. And we here try to see whether this measure of clustering performance correlates with the ground truth performance. Let's dive into the results a bit. On this slide, you can see the average and standard deviation clustering results across all algorithms for the 3 different physiological measures used. That is EEG, skin conductance, and heart rate. And as maybe not unexpected based on earlier research, EEG here performs best with an average clustering accuracy of 73%. However, skin conductance and heart rate perform worse with lower clustering accuracies that are not significantly above chance level. We then also investigated if combining different measures in a multimodal fashion would increase clustering performance. And as you can see on the slide, in most of the cases, it did. When combining EEG with any other measure, that enhanced clustering performance base compared to the best performing unimodal metric, as you can also see here on this slide. However, combining heart rate and skin conductance still does not lead to above chance level clustering performance. When comparing performance between algorithms that were directly applied on their distance matrices or after applying a certain mapping algorithm, we can see that in general the performance was higher after applying a mapping than when directly clustering on the distance matrices. So, what do these results actually say? The aims of this research were to correctly identify groups of individuals with shared attentional instructions based on physiological synchrony in EEG, skin conductance, and heart rate. As you can see, is that EEG performed best, whereas skin conductance and heart rate performed around chance level. We also can note that combining multiple measures into a multimodal measure increases the maximum performance, but also increases robustness to different types of algorithms, as the performance varies less between algorithms than when using only one physiological measure. When investigating how clustering performance depends on a specific unsupervised learning technique, we can first note that mapping the distance matrices before clustering leads to higher classification accuracies than when clustering directly on the distance matrices. We can also note that performance is strongly dependent on algorithm choice, especially in a unimodal fashion. And unfortunately, our unsupervised evaluation, silhouette coefficients, did not work well, as it did not correlate well with grounded performance. However, one solution may be to go to a multimodal approach, as that at least leads to more robust clustering across algorithms, and you're then less dependent on algorithm choice for the results. In our case, the PCOA seemed to be the most appropriate mapping, and spectral clustering also performed generally well. However, we do not know how these results translate to other studies, so that is good to investigate in future work. For now, I would like to say keep in sync and thank you for listening.